Hello everyone. Today our focus is autoencoders, which are a specialized neural network used for unsupervised learning. In today's tutorial, our goal is to understand how this network helps us extract robust features and effectively mitigate noise, which is vital for quality control in applications like image processing or signal processing. The fundamental idea is that we corrupt a clean image with random noise and then we train an autoencoder to reconstruct the original uncorrupted version. In forcing this repair, the network learns the true underlying structure of the data. We call this compressed representation the latent dimension. Our lesson has two parts. One will use a MNIST visualization to clearly show the training steps. We will observe the forward pass, how we calculate the training error using the loss function, specifically the mean squared error, and how the error drives weighted updates through gradient descent. In part 2, we move to the practical side. We go through a PyTorch code line by line. We will analyze the network's layered architecture, the technique for Gaussian noise injection, and the configuration of the data loaders for the MNIST dataset. By the end, you will master both theoretical principles and the technical implementation of this powerful deep learning model. So, let's begin our work. First of all, what is an autoencoder? It is a neural network designed to replicate its input at its output. Its structure is symmetrical, composed of two main parts, the encoder and the decoder. Data enters through the input layer. In the encoder section, it gradually compresses this input, passing it through the smaller and smaller layers. The crucial point is the latent space or bottleneck layer, which holds the compact, high-quality representation of the input. Following this, the decoder section takes this compressed code and progressively expands its back. The final output layer attempts to perfectly reproduce the original input data. The entire process is simply input, compress, reconstruct. The network learns by minimizing the difference between the input and the final output. So, why use autoencoders? Why is this reconstruction task useful? The autoencoder's ability to compress and reconstruct data enables several powerful applications. First one is dimensionality reduction. By using the latent space, we can reduce data size while keeping the most critical information, saving storage and computation time. Second is denoising. Autoencoders can be trained to recognize and remove noise by comparing corrupted input to clean outputs, a process we call denoising. The third is anomaly detection. They are excellent at identifying outliers. If the network can't accurately reconstruct an input, it likely represents an anomaly or a rare event. The fourth use case is feature learning. It is crucially the encoder extracts the most important features of the data, which can be then used as inputs for other supervised. The key difference is that autoencoders learn powerful data representations without relying on human-provided labels, making them ideal for pre-training models. To summarize the core concepts of the autoencoder, it learns compressed representation, operates in an unsupervised manner, is highly useful for dimensionality reduction, and serves a distinct purpose from supervised CNN. We are building a denoising autoencoder using PyTorch. So first of all, we will import all the necessary libraries. We are import the torch, then we import the torch.nn as nn to create the network layers, and then we will import the torch.optim to use the optimizer and some utility data loader functions, and the torch vision for using the MNIST dataset. This is same as we explained in our previous video. Then we need a simple numpy library to use some numerical calculations. Next, we will set random numbers to ensure the results are reproducible, And finally, we will check and confirm if we are running on powerful GPU or a CPU. Next thing, we need to create some variables, which is batch size of 128 and learning rate 0.001 and 5 epochs for minimum training, and a latent dimension is 32 and noise factor we will be adding to our MNIST dataset is 0.3. Now we are going to define our autoencoder model, and our autoencoder model class is simply derived from the nn.module just like before, and we are initializing it with our layers. And first of all, we will create an encoder model. Inside this encoder, it is simply a sequential layer, and this encoder will be reducing the dimensions from 785 to 128 then 64. And how we do that, we first of all create a linear layer by 28 by 28, which is the actual size of our MNIST dataset, and we are expecting 128 dimensions output. Then we apply a ReLU activation function to that. After that, we created another linear layer which will accept this 128 neurons and produce 64 outputs neuron, and we apply another linear layer which will take this 64 in neurons and produce a required latent dimensions, which is 32 in this case, and apply a ReLU activation function. Now we have a proper encoder intact with just simple linear layers. We can change these layers in according to our need, but for the simplicity we keeping this to the linear layers. Then we are creating our decoder section, which is another sequential nn sequential, and it will expand the architecture from 64 to 128 then back to 784, and we will get our original image back. So how we do that, we create another layer from taking the latent dimensionality, which is 32, and we expand it to 64, and we apply our ReLU activation function to learn the non-linear activations. And then we create another layer by 64 to 128, and similarly we will apply a ReLU, and then we create another layer, and finally we will be creating a sigmoid layer. This activation function will be providing the output between 0 and 1. So how we do a forward pass, we will simply creating a forward pass like this, and inside that forward pass, first of all, we will creating a view for the flatten input layer to flatten over X input, which is an image, and we will create a one-dimensional array. Then we will pass this one-dimensional input to the encoder section, and encoder will output the latent space. We pass this latent space to the decoder section. The decoder section of this neural network will decode the encoded latent space and expand it back to our original X input and possibly the reduced noise. And then what we do, we create the reshaping to the back 28 by 28 image. We do that by using the dot view function, and we will decode dot size, and instead of -1 we'll use here 1, and then we provide the dimensions 28 by 28, and we will return this decoded image back. So that's how our autoencoder simplest model for denoising the MNIST dataset would look like. Now it comes the main heart of the denoising aspect. This add noise function takes our clean images and simply adds a random Gaussian noise to them. The torch.clamp function line ensure that the pixel values stay valid between 0 to 1. So that's return a noisy image. And then we load the MNIST dataset using transformer.compose, and with the dataset.mnist train dataset, and similarly we load the test dataset. And here it comes the data loaders, and we provide the batch size and the shuffling is equal to true, and similarly the test loader use the test dataset and batch size and shuffling is false for the test loader. We only need the shuffling in the train loader. Then we simply run the loop of we print the length, and we first of all need to run this block so that our add noise and transform.compose would be valid. And here we are loading the MNIST dataset, and once it complete we are ready to use our data loaders. And here you can see the training samples are 60,000 and test samples are 10,000. Then we are simply initiating our autoencoder model from here, and it sends to the GPU if available, otherwise CPU, and define the training components. We use the mean square error loss as our loss function, which measures the difference between the clean image and the reconstructed image. Then we use the Adam optimizer. This is an efficient optimizer for our current task. The train function comes for the training part. This is for the model training. This train function is where the learning happens, and for each batch we first call our add noise function like this. We run the for loop to our batch, and we move it to device, and then for each batch we use a add noise function and we get a noisy data out of it. This noisy data is passed forward through the model. We then calculate the loss by comparing the model's output against the original and clean data. We use the forward pass, and we pass this noisy image through the model and get the output. Then we calculate the loss, and this loss criteria is from output and the actual data, not this noisy data. Remember that, because we want the decoder model to learn to create a image which is similar to the original data without any noise. So that's why we are comparing and calculating the loss through the actual clean data set. Then we create a backward pass for optimizing, and we run the optimizer, and the loss is back propagated to adjust the model's weight. That's how we simply print our current loss, and then we print our average loss. That's how the overall training loop will happen. So that function is created. We create a similar function for test, and we first of all evaluate the model, and this function is similar but operates in evaluation mode. So without updating the weights, our main training loop simply iterates through over 5 epochs, printing the loss after each epoch, and this loss should steadily decrease as the model learns to denoise the image more effectively. And finally we see the results using the visualize. We created another visualize result function, and this is the method of visualizing the results. This function takes a batch of test data. For each image we display 3 rows: the original, clean image, and the noisy input. The model actually saw and the denoised output reconstructed by the autoencoder. You can clearly see how the network successfully learned to suppress the noise, and we also generate plots to analyze the training process and the training curves. That shows how the loss decrease over epochs and the latent space. Visualization shows how the autoencoder clustered similar digits together in its compressed 32-dimensional space. We use PCA to reduce this to 2D plot. The final step saves the trained model for the later use and display a summary of the successful denoising task. The denoising autoencoder has learned to extract the meaningful features from the handwritten digits, ignoring the random noise. So these are the plots that we get. Here you can clearly see we pass this original image, and we corrupt this image using a Gaussian noise, and this is the output of the over encoder-decoder model. So this is the train test loss, and here is the latent space visualization in the 2D space. So these are the results, and image denoising, dataset MNIST, and architecture is 784 to 128, 64, 32, then back to 64, 128, and 784. The training time is approximately 2 to 5 minutes on CPU for 5 epochs, and the final test loss is 0.0242. The autoencoder learned to remove the noise from images, and you can check the generated images to see the denoising results, which are that. So that's all which I want to talk about the autoencoders and how they denoise an corrupted image.